Hello everybody, here is our video on arc length, which also is called the length of curve sometimes. And the question that we're considering here as a motivation for this video is if we have a curvy graph here, how would we be able to find the length of this curve if we didn't know calculus? So if we had a graph that was just a straight line, then it would be very easy to find the length of the curve. It's not even a curve anymore. We could find the length from A to B very easily. We know the distance formula. But the thing is, this is curvy here. It's not a straight line. The only way we would be able to do it is if our curve was made up of a bunch of straight line segments. But wait a minute, in calculus there's this thing that says if you zoom in enough on a certain part of a graph, it appears to be straight, and that is called local linearity, one of your first videos here. So even though we have a curvy line here, what if we broke this up into a bunch of little pieces and can zoomed in so much that it turned into a straight line? Write down the general process here. What we're going to do is we're going to break our curve up to many straight line segments here, and then we're going to add up the lengths of each segment. And we know how to find the length of each line because we know the distance formula. And the distance formula, make sure you write this down, because what we're going to actually do is derive a proof here. Everything in calculus has a proof, and we don't prove every single theorem because some of them are very lengthy and tedious. But this one is very manageable, and it actually is a good review of another theorem you know. So we're going to go ahead and prove how we find the length of this curve. So again, I am going to break it up like I said. And let's consider just like one little segment that, now let's do this one here, whoop, this guy right here. So I've broken it up and I'm zooming in really far into one of my curves so that I'm looking at like this here. So this is the one I'm zooming in on. So go ahead and redraw this in your notebook. Zoomed in though. And what we're going to do, because local linearity, again, says if you zoom in enough, a straight line or a curve will eventually become a straight line. So I've overemphasized the curve here just to show that this curve will eventually become the secant line. So right now, our secant line is going to approximate the curve. So secant line approximation. And because I'm considering the curve to be a straight line on a tiny width, the key is delta x is really small. That's why I can even say this. So because I am considering it to be a line, I'm going to go ahead and find the distance of it. Okay, so we are zooming in, and I'm going to find the length of a sample spot. Now this curve here, I didn't specifically say it before, but we are assuming that it is continuous, and we're also assuming that it's differentiable. Because it's continuous and it's differentiable, there is a theorem that we've learned before that applies here. So a continuous and differentiable curve, that means the MVT applies. So in the corner here, I'm going to write the MVT, because not only am I going to use the distance formula, I'm also going to need the MVT at some point. So let's write what the MVT says, the general formula, and then we're going to slightly modify so that our variables match up. So here's the MVT. All right, so let's take our distance formula and let's slightly modify so it's going to work for us here. y2 minus y1, I'm going to call it delta y, which is this here. x2 minus x1, I'm just going to call it delta x, the length right here. So I basically have a triangle right here. So let's take our distance formula. So the length of this one little segment that I'm zooming in on, remember this is just for one little sample segment, is going to be delta y squared plus delta x squared. So just follow along with me as we do this and pause it if you need to get caught up. I'm just going to rearrange this here because at the end, in order to get the desired formula, delta x should really come first. So I'm just switching delta x and delta y here. Now, delta y, let's take a look at this here and pause. I'm going to replace this with something. Let's go back to the mean value theorem. And f of b minus f of a over b minus a is really just a secant line slope. And f of b minus f of a, all that is a difference in y values. And b minus a is just a difference in x values. So check it out. Now our variables all match here. And let's go ahead and solve for delta y because we're going to do substitution. So if I solve for delta y, I'm going to multiply each side by delta x. So what I'm going to do is take this right here, and I'm going to plug it in for delta y. So let's rewrite it. And we have delta x, that's not changing yet, plus f prime of c, and I'm going to use x here so that our variables are all the same. Same thing, really. And I'm going to square that. If I have two different things multiplied each squared, that means they are each, or if I have two things multiplied squared, that's the same as saying that each of them is squared. So let's write it like that. And now let's take a look at this and notice that I have two terms here. I have this term and I have this term. And both terms share something, and it should be obvious to see that they both share a delta x squared. So what I'm going to do is factor out a delta x squared. And if I do that, I'm left with a 1 there, and I'm left with a f prime of x squared here. And if I have two things multiplied, this, and they're under a square root, I can take this out because I can do the square root of delta x squared. The square root of delta x squared is just delta x. So now I have delta x times this cannot come out of the square root. Watch your parentheses and your notation here. Okay, so this right here is the length of one partition. So make sure you label it like that. And by one partition, again, remember, that means like one itty bitty thing. And ideally, what we did is we broke this up into tons of them, and we want to add all of these up, like almost infinitely many. So what we're going to do is think, okay, what in calculus allows us to add up lots and lots of things? But before we even get to the calculus part, let's just say I'm going to use a sigma to add. So what I'm going to do is add up all these lengths, like I said. So I'm going to do a sum of all the lengths. And let's throw the delta x at the end. So I'm taking this and I'm putting it here, and delta x is at the end. Now, this right here, label it as a total length approximation. So our total length approximation is equal to the sum of all our individual line segment lengths. But the thing is, I want this to be more than approximation. I want it to be exactly the length of my entire curve without settling for an approximation. I want the real deal here. So ideally, to get it exact, we would need infinitely many partitions. So to get an exact area, what we're going to do is we need the limit as... Now, in order to get infinitely many widths, let's think about what has to happen. In order to fit infinitely many widths from here to here, the number of partitions has to go to infinity. And in order for that to happen, our width of each partition needs to go to 0. Because the smaller the widths, the more that you can fit in. So what we need is delta x to go to 0 to get infinitely many partitions. So let's just do a limit, and once again, limits are coming in to save the day. Limits are needed for derivatives, limits are needed for integrals with Riemann sums, limits are needed for length of curve, and guess what? Limits are going to be needed for series in about a month. So limits are the backbone of calculus, and they're amazing. So we're going to do the limit of the sum, and we're going to let I go from 1 to n, where n is the number of partitions, just like before, n was the number of rectangles in a Riemann sum. And we're just going to add up the length of one individual partition. Oops, like that. Okay, but remember, mathematicians were lazy. They didn't feel like writing this over and over again, so they came up with this integral. And this should look familiar because we've done basically this whole process before with Riemann sums. So I'm going to replace the limit as my widths go to 0 of the sum of all the widths with integral, because integral means add up infinitely many things. So add infinitely many things. And what I'm going to do is I'm going to add up all the lengths of my curves, which is represented by this. And these guys get tiny, tiny, tiny little baby widths on the xy axis. And in calculus, we call that dx. So again, you replace delta x with dx. And believe it or not, we just derived our formal theorem. So that was cool. That's not too bad of a derivation. So this is the exact length of our curve from A to B. So I'm going to pause now, and the next video will be the examples.